So are you guys okay with kind of where we went yesterday? So yesterday we learned what the greatest integer function was. And then after we understood kind of how the parent was shaped, we went through the effects of putting a negative in a different place in the equation, and we kind of thought about it in multiple ways. We thought about how that negative would affect the outcomes in the table, and then what that meant was happening on the graph. So when the negative was outside of the greatest integer function, we knew that was changing the value after we had rounded it, so that would be like changing the y values, and changing the y values to their opposite is like reflecting over the x-axis. Okay? Whereas when we had the negative inside, like this here, okay? When we had the negative inside affecting x, you would use the negative with the original x value and then do the rounding. So it would be the x value that got changed before you ever rounded it, which would change all of these to their opposite. And we talked about changing x to its opposite value being like a reflection over the y-axis. Is that okay with everybody, that idea? Okay. All right, so today we want to look at numbers in these different spots and how they affect it. We talked a little bit, maybe in the other period, about the fact that in absolute value, how did we deal with this? If there was a number in here and this was an absolute value function, what did we do? So if this was an absolute value function, not a greatest integer function, and you wanted to graph it, and we're only used to having a, h, and k and no number inside multiplying x, how did we deal with it, Ethan? Yeah, we would just factor it out, okay? But there's a problem with trying to do that in this instance, okay? For example, let's say you plugged in, if we could just factor it out, then number 12 and number 13 would basically be the same problem, right? Okay, but here's where they differ a little bit. So you don't have to write this down, but just to kind of confirm in your mind that these are different situations, I want you to think about calculating this versus calculating this when we plug in something like 0.8. Okay, let's say I plug in 0.8. In the first part here, 0.8 is going to be rounded before it's multiplied by 2. And what is 0.8 going to be rounded to with our greatest integer function? 0. So 0.8 gets rounded to 0, and 0 times 2 turns out to be 0. In the second version of the function that's up here, if I plugged in 0.8, 2 would actually be multiplying 0.8 before I did any rounding. And what is 2 times 0.8? 1.6. And then what would 1.6 be rounded to? 1. So do we see how those are different here? Different values, which means we can't actually treat this like absolute value. We don't have a simple solution. We can't just have the a, the h, and the k where the a can always be taken outside. We have to now acknowledge that these two numbers do two different things to our function. There's two different outcomes. So this is like an a value, just like in the absolute value function, but this one is not. We often use b in our class to represent the position of this number. And in the greatest integer function, we cannot factor it out. So are you starting to see the main differences between like absolute value and greatest integer function? Depending on what the function itself does, sometimes you have more freedom and sometimes you don't. And in this case, we don't, all right? So now let's talk about how these graphs would look. We're going to plug in some points just to get the idea. And then we'll kind of summarize for ourselves, like, oh, then what actually happens? Like when there's a number out here, what is it controlling about those steps that we see with this function? Versus when there's a number in here, what is it controlling about the steps that we see with the function? All right? So we're going to make a table. Again, our goal is not to keep graphing like this. However, well, we're just kind of like figuring out what's going on. We're like experimenting. We're going to stick with what we know, which is plugging in points. And when we're done experimenting and we have a conclusion, hopefully we don't have to plug in points anymore and we have kind of like shortcuts. Really, it's because you understand the mathematical behavior. You can quickly graph it without that. So if you plug -1 in here, -1 stays as -1 times 2. So we get -2. 0 stays as 0, 2 times 0 is 0, and 1 stays as 1, and 2 times 1 is 2. So I have a point at -1, -2, a point at 0, 0, and a point at 1, 2. Then the next thing I'm going to do is I'm going to plug in things halfway in between. Half is particularly interesting to me for two reasons in this problem. Reason number one, I want decimals in between to see how they're being rounded, okay? But the reason I really like a half is because there's a 2 in the problem. So like 2 and 1/2, if they just multiply together on their own, usually make another integer. So I'm kind of curious to see how that happens here. So do you guys understand my motivation? I want to plug in decimals to see how they're rounded, but a half is a really interesting number to me here because I want to see how it interacts with the 2. Like, does it make a new integer or not? And what happens? So I'm going to go ahead and I'm going to plug in positive half and negative half. And then if we have to, we can plug in some things around that to kind of confirm to ourselves what's happening. So if I plug in positive half, okay, so remember that's getting plugged in right here for x. The first thing that's happening to it is it's being rounded, and then it's being multiplied by 2. What is half being rounded to? 0. And then 2 times 0 would be 0. So at a half, I'm still at 0. Oops. Okay. Yeah, it doesn't want to stay on the. So like right there. It's not a significant point. I'm just plotting it so you guys understand like visually what we have just figured out. So actually, let's try something else like closer to 0, further from 0. Okay. So let's say I try like 0.1. What's going to happen to 0.1? It's going to be rounded to 0, and then 2 times 0 is still. What's going to happen to any number that I pick between 1 and 0? The first thing that's going to happen to it is rounded to 0, and then when 2 multiplies 0, it will still be 0. So do you guys agree that I'm just getting a bunch of points along this line right here? That all these x values from 0 to 1 are just staying with a y coordinate of 0. However, I know when I plug in 1, it jumps up to 2. So there I'm going to put that open point. So that first part of it kind of looks a lot like our parent function, right? Just have this one constant there. Except for when I got to 1, normally when I plug in 1, it jumps up 1 unit vertically, right? But this time when I plugged in 1, it jumped up 2 units vertically. Okay? And so then let's see what happens here. What about if we plug in negative half? What does negative half get rounded to? Negative 1. We have to be real careful with it, right? Like it's between 0 and negative 1, but we can't let it be bigger than itself. So it gets rounded to negative 1. Okay. And negative 1 times 2 is negative 2. So negative half, negative 2 is a point on my graph. What will every number that's in between 0 and negative 1 be rounded to with our greatest integer function? Negative 1, right? They'll all be rounded to negative 1, and then every time we multiply those by 2, they'll turn into negative 2. So anything you plug in here is going to end up with like a negative 2 y coordinate. So I'm getting all these points along here until I plug in 0. I know that then it jumped up to 0. So we actually have enough here to fill in our steps because we have beginning and ending. So how long should each step be as we complete this graph? Every step should be 1 unit long horizontally, okay? And do they go in the normal arrangement of steps? Like do we start at the left with a filled in point, go towards the right and end with an open point? Yes, and then we jump up to the next one. So it follows the normal kind of staircase that we saw in the parent function. Horizontally, every step is 1 unit across still, but what changed from the parent function? Vertically, we go up 2 now every time we go to a new step instead of going up 1. So like this next step I can predict would be right here, and the one after that would be up here. The one below this one would be down here. Okay. So what is an a value doing in the greatest integer function graph? So when I say a value, I'm saying when you have a value outside of the greatest integer function, like 2, what is that telling you about your graph when you draw it? Okay, so it's going to change the amount of space vertically between the steps. Is that okay with everybody? So if this wasn't a 2 and it was a 5, what would you have expected to happen on the graph? 5 units apart, right? So like our first step would have still been here, but the next step would have been like 5 units above it. Okay? What if this was 1/3 instead of 2? You don't go up 1/3 because then your steps wouldn't connect. If you go up 1, so if I drew a step and then I went up 1/3 to the next step, I would be missing a bunch of my x's in my domain, but we're allowed to plug in every x. Okay? So what would happen if you had a 1/3 here instead of a 2? James? Okay, here. And then do what? Up, how much? Up 1, okay. And then if you go over 3, you're still disconnected from your graph. I think Ethan knows, but he told us a couple things already. Yeah, Karen? Yeah, all you do is separate your steps by 1/3 of a unit. Okay, so your graphs for your step functions, if there's an a value, do not change from this pattern. The only thing that changes is how far apart they are. If I had a 2 there, these are 2 units apart. If I change it to a 1/3, it would still look the same, except for they would only be 1/3 of a unit apart. Is that okay with everybody? So the a value here is not the same as the absolute value function. It literally only controls vertical separation of your steps. It has nothing to do with moving horizontally. Is that okay with everybody? All right. So now look at, and okay, if you guys are having trouble categorizing, like how would I know it's vertical or horizontal? Again, think about our original function. When you're doing something after you've already rounded it, in your parent function, the numbers that were after you rounded it were the y values. So if something's happening after the rounding is done, it's like it's affecting y. So that's why that 2 is only controlling the vertical, okay? So this 2 here in this next function is inside. And so we're going to see how that's different. We know it's different because we plugged in a number and saw a different value. But the question is, what does that control about the graph? Okay. So we're going to do the same thing. We're going to make almost the same exact table. And at first, it looks almost the same because if you plug in -1, it multiplies 2 and you get -2. And so because it's an integer, we don't have to do any rounding. With 0, we get 0, and with 1, we get 2. These are the same 3 points that we started with last time. And this should also kind of confirm for you the idea that plugging in points is not the end-all be-all, because if you don't know certain things, you would get the impression here that this might look just like the other function. Okay? So now let's see if we plug in those points halfway in between. So first, let's focus on the points that are between 0 and 1. Okay? So I'm going to first plug in a half. So when I plug in half, what's the first thing that happens to it in this function? You plug in half for x, what happens to it? It gets multiplied by 2. What's a half times 2? 1. Now it's a whole integer that doesn't require any rounding, so this actually makes 1. Okay. All right, so everything between 0 and 1 here doesn't stay the same because we found that it changed, right? They didn't all end up being 0 or 2. We already found one that would end up being 1. So I'm going to kind of like take back my idea of grouping those all together. And I'm going to say, okay, let's try to focus on things between 0 and a half as x value. So let's say we plug in like 0.1. Okay? What's 0.1 times 2? 0.2. And then when we round that, it gets rounded to 0. Is there any number, zooming in a bit, sorry, is there any number between 0 and 0.5, so not 0, not 0.5, but anything between them, that when you multiply it by 2, you're going to get something bigger, like 1 or bigger? No, because our half is the place that happened, right? 2 times 0 is 0. 2 times a half is 1. 2 times everything between 0 and a half is going to stay between 0 and 1. Do you guys agree with that? And any number that's between 0 and 1 would be rounded to 0. So all of these are going to be 0 until we get to half, and half is going to be a key value that we're going to need. So on this graph, I'm zooming in because it's hard for me to draw it. I just figured out that everything that's between 0 and a half stays at 0, but at a half it jumps up to 1. So there's all my x values between 0 and a half staying on that x-axis at 0, but at a half I'm jumping up to 1. Is that okay with everybody? All right, so now the question is, what is happening between a half and 1? Okay, at a half times 2 is making 1, and 1 times 2 is making 2. So because those are the integers, I'm pretty certain I can lump everything between there. There's not any integers in between that they would become. So everything between 0.5 and 1 is probably going to behave the same way. So let's try something like 0.8. Okay, we already did this one. So 2 times 0.8 becomes 1.6, and then 1.6 would be rounded to 1. Okay. If you did 0.9, you get 1.8, which would be rounded towards 1. If you did something like 0.6, you get 1.2, and it would be rounded to 1. So everything between half and 1, all those x's, end up producing 1s as their y values. So in this graph, every x between half goes 1, produces 1. So I'm doing all these points up here to make this bar. And then at 1, it jumps up to 2. So I have 2 steps now. That should be enough for me to determine a pattern of how I would continue drawing this graph. So someone describe to me how I can continue drawing this graph. Taylor? Good. Okay, so every half unit horizontally, that's the entire step now. So the steps aren't 1 unit long, they are half a unit long horizontally. Okay, so I started at 0, 0, made a step half a unit long, and then what's the vertical distance between the steps? 1. So I jump up 1 unit. Start my new step, closed end point to an open end point. It's half a unit long, and then I jump up 1 unit. So the next step would look like that, half a unit long. Then it would jump up the next unit. It'd be half a unit long. It would jump up the next unit. It would be half a unit long. Okay, and you can work that same way backwards to get steps that direction if you want. Okay. So what does a number in this position control about our graph? So this 2, different than the 2 before. The graphs look different, the numbers rounded differently. How would you describe, like, what is this number controlling about our graph? Andrew? Good. It's controlling the horizontal length of the step. Is that okay with everybody? But what's weird about it? How long did the step end up being? A half, right? But the number in the problem was 2. Okay? Take a second in your group and see if anybody knows why that's happening. Cute. Okay, ideas. Who thinks it's not an easy concept to explain verbally, okay? But who thinks they have some ideas to lay out there about why when there's a 2 in the equation and I want to do something with 2, I see that it controls the horizontal length of the step, but it's coming out to be 1/2 and doesn't just like match the number in the equation. Anybody can lay out any ideas? She's pointing at you, Sam. Will you throw anything out there for us?
Maybe that it segments each x unit. So if it's 2, then there's going to be 2 different segments in each x unit.
Okay, so that's a really good way of thinking about it, and we'll see how that connects. Did you guys get what he's saying? What we used to think of as 1 x unit, okay, like that it takes 1 whole length here to do that something. he's now saying there's a 2 there, and it's basically saying, well, 2 of those now fit in the space that there used to be 1. Okay? And so that is a good way of thinking about it. Okay? What else did people have that fits kind of that idea but was said slightly a different way? Grace?
Because every half x value gets rounded up to the next. It's like 0.5 would be 1, 1.5 would be 2.
Yeah. So like he's going with like an interpretive of like what the number might be in the equation. And I like that you're going with like numerically look at what's happening. Because we're changing the number before it's rounded, okay, we are affecting the outcomes that a half actually becomes an integer in our greatest integer function. We don't normally think of it as an integer because half is not, but because it's being multiplied by something, it actually becomes an integer. So there are some fractional things in between our two integers that then could become integers, okay? Other ideas? Cooper, are you willing to say what you said at your group too, or no? I did hear you.
So, for the graph, for the graphs, each line, each segment moves up twice as fast since the inertia is smaller.
Yeah. So this is just another way to think about it, okay? X got a coefficient of 2, and the 2 does mean 2. It means you hit X values twice as fast as you used to hit them. But think about what that means. If you drive to school twice as fast as you normally do, how long does it actually take you to get there? Half the time. Is that okay with everybody? Mm-hmm. So X is moving twice as fast, but that means you only have to go half as long as you used to. Does that make sense to people? Okay, so it's not a simple idea, but I'm hoping that hearing their ideas, okay, that X is going twice as fast. The 2 does mean 2. It just doesn't mean 2 on the graph, okay? It means it's going double time, which means the length of the line only has to be half as short because, like Sam added to that, we are now fitting 2 segments in one. And then like Grace said, you can see it numerically when you're plugging it in and you can see that values are changing there. Is that okay with everybody? So if you want to make a note, this looks real cute now, right? It's like I've scribbled all over it. You want to make a note that this 2 is controlling the horizontal length of the step. However, we really want to use the reciprocal of it because if X is moving twice as fast and we're reaching those values twice as fast, our steps only have to be half as long, okay? So what if there was a 5 in here? What if it said like 5x? What would that mean about our steps? Ethan? Yeah, each segment would only be a fifth of a unit long. And at that point, you just might want to scale your graph differently, right? Because I don't know about you, but I want to, a half was one thing and I could zoom in. But if I had to scale like a fifth, honestly, I'd be like 1, 2, 3, 4, 5. That's 1 unit. And then I could just draw the steps like this, okay? All right, that kind of idea. Now, what if it wasn't 5 in there? Instead, it was like 1/10. Andrew? Each step would be 10 units long because X is reaching the values at 1/10 of the rate that it used to. In other words, it takes 10 times longer to complete the 1 step, okay? Does that make sense to everybody? Mm-hmm. All right. So I know it's a weird idea. We love that the numbers are right there in the equation, but it sucks when you can't use them at face value, right? Like we can't just take 2 and use 2. We have to actually process what it means in the equation converted to the graph, and it doesn't look exactly like you might expect initially, okay? Is that all right with everybody? Mm-hmm. Yes. Okay, so I have a Cartesian. You don't have to draw all the steps. If you draw a significant amount of the steps, I'll understand that you know that those keep going on infinitely. Okay?
How would you write the exercise?
Oh, we're going to do that right now. Yeah. Okay, so characteristics of the parent function. So you're looking at the parent function graph. And so let's talk about this. H and K are going to be set up the same way they were in your absolute value function. So actually, if you look at the top of your Cartesian catalogs give you the function in its format. So you see just like absolute value, A, H, and K, but the new thing you see in there is B, and that's because with absolute value, we could kind of like ignore it if it was in there because we had a way to get it out. So we would just take it out and just always have A, H, and K, but we saw we cannot do that with greatest integer function. They are different. We can't just factor stuff out. But notice that we still separate the B value from the X minus H because H and K will only do what they do if we look at them exactly the way we've studied the way that they move the graph, right? And the way we looked at H was only if it was part of X minus H, not 3X minus H or a half X minus H, just X minus H. So we still factor it out. It just all has to stay inside the greatest integer function bars, okay? So your H and your K here would be what values for the parent function? So think just like absolute value. In the H and the K spots, what are the values of this function? 0, 0, okay? 0, 0 isn't really a vertex in this case, but it's kind of where we start our graph. So I like to think of it as a starting point. Okay. That's where like that first initial step starts. So it can still shift it left and right or up and down if you have H and K values. All right, let's start with y-intercept because it's a little easier than x-intercept. What's our y-intercept on this graph? Yeah, 0, 0 is the only place it intercepts the y-axis. How many x-intercepts are there? Yeah, there one branch right here contains x-intercepts, but how many points are there on the x-axis between 0 and 1? Infinitely many. So we would say there are x-intercepts at all x values between, and then we'll write it like an interval. So including 0 up to 1, but not including 1. That's the only way we can say that there's like an infinitely many things, is to try and like give them an interval. So you couldn't list it out, right? You'd be there forever, okay? All right, domain values. So we talked about this with the parent function already. What can you plug into this equation? All x's, right? It'll round them, but you can plug them all in. So all reals. And then what did we say the range was? Ethan? Good. So it's like -2, -1, 0, 1, 2, and infinite in both directions. That set is all of the integers, and we write that set like this. So if you don't remember what that is, make a little note for yourself so you get used to that notation. All right, now increasing interval and decreasing interval. Here's the thing. I know that our graph increases over time if you look at it from left to right, that the steps seem to be going upward. But an increasing interval means that if you're on the line of the graph and you're moving towards the right, you're also moving up. That doesn't happen here. You move constant, and then there's a jump, but then you move constant. So you're never on the line and increasing. Does everybody understand that? When you're on the line, you're only constant. So technically, this graph does not have any increasing or decreasing intervals. Is that okay with everybody? That the increasing and decreasing intervals aren't like looking at the graph overall and be like, well, it ends higher than it started. It's like when your pencil is on there and you're moving left to right, to be increasing, you must be moving up, and to be decreasing, you must be moving down. And that doesn't happen. Okay, you could have a part that's disconnected if it moved, like some of our piecewise graphs had a part where like we were increasing, then we weren't doing anything, we were constant, and then we were like increasing or decreasing again. This graph is all constants, so there's no increasing or decreasing interval. Okay? Is the graph 1 to 1? Is it a function first? Yes, so if I look at the graph, it passes the vertical line test, it's a function. Does it pass the horizontal line test? No, it epically fails at every integer. Because how many points are there again between 0 and 1 where it's on the x-axis right here? Infinitely many. So even though I'm only hitting one branch of my graph horizontally, I'm hitting infinitely many points on that one branch, which is much more than 1, which means it violates that test, and so it's not 1-to-1. Okay? The rate of change here is not something that we discuss. Neither is the axis of symmetry. Doesn't have any. And again, this function doesn't have asymptotes. Does it reach a minimum value? No. And does it reach a maximum value? So these are none. So we're going to do one more example together with the characteristics. Because really, you guys have only graphed parent functions and really individual ones. Look at the example that we're going to work on. I think we need to talk about it. It does look really confusing. Okay, are you guys with Madison here? Does this look really confusing? All right, so first thing that should happen in your head, you see the brackets, okay, and you should think, what is it going to look like? Steps, right? So the first thing that's going on in my head is this. I'm just going to draw a couple steps, but in general, I want an outcome that looks like this. Okay? And normally, what are the characteristics of this steps? Normally, where do we start at? 0, 0. That my starting point would be 0, 0. And how long would my steps be horizontally? 1 unit. Okay, parent function-wise. And how far apart would they be vertically? 1 unit. Okay, that's my normal expectation, and then I'm going to adjust that expectation based on what's in the problem. Before you adjust your expectation, you need to see it in the format that we want to see it in, and the format we want to see it in is like this, okay? So right now I know that my A is 3, okay? What's my B value? -1/2, that's correct. What's my H value? Okay.
-2.
It's not 2 or -2.
Oh, no.
Why is my H not 2 or -2? Cooper?
Because the b multiplies both the x and the h.
Yeah, you don't have an x minus h quantity right now. You guys have a -1/2 x plus something. Did you study on your little investigation what -1/2 x plus or minus something did to the graph? No, you studied x minus 2's and x plus 2's, which means you need your own little quantity where it's just 1x, not with the -1/2 multiplying it. So I need to separate that out before I can fully identify my h value, okay? So I'm good with saying A is 3, B is -1/2, and K is 2, but don't make assumptions about h till you've really made the equation in the format in which you studied it. If you put new things in there and it's not the way you studied it, it's going to do different things, okay? And so we have to get everything. We don't want to study it 12 different ways. We want to study it one way, and we did, but that means we have to transform everything to look exactly like that to really understand what's happening to it, okay? So when you factor -1/2 out, you either know -1/2 times what makes 2, or you need to go off on the side of your paper and say, I had a 2, I'm dividing out -1/2. 2 divided by -1/2 is the same thing as 2 times -2/1, which is -4, -4. So I'll ask again now, what is my h value? 4, okay? So good pull back there at the beginning. Right, so how do I interpret this information? The first thing that I would look at for you guys is the negative. The negatives here are difficult. You remember how they flip and reflect the graph and everything? So we have a negative happening with our b value inside of the greatest integer function. That meant it was affecting the x values. And when you change x from a positive to a negative, what are you reflecting over? If on the graph, look at the graph, you change positive x's into negative x's, and negative x's into positive x's, what are you flipping over? Over the y-axis, okay? So this negative here is a reflection over the y-axis And the reason I say that is that's going to change what I think my picture looks like. Okay? That I'll still have a starting point, but everything's flipping from like the right side of how I drew it over to the left side. So instead of this step going that way, it's now going to go like that. Okay? Not over here anymore. And then this step here is going to flip over here, and it's going to go like that. Is that okay with everybody, my change of expectation? So I now expect to still start at a point, but instead of going to the right one, ending it, and going up one, I expect to go to the left some amount, and then up to the next step, and then to the left, and then because of the reflection, all right? And now I want to put in the amounts. If I just know a starting point, how long to draw my step, and how far apart to draw them, I have a general idea of how to sketch it. Okay, so how do I get an accurate starting point? Am I still going to start at 0, 0? No. Okay, so someone new, raise your hand and give me a new starting point that we're going to start at. Peyton?
4, 2.
Good. 4, 2. Someone else explain where Peyton's pulling out those numbers from. How does she know the starting point's at 4, 2? Jay?
The H and K values.
Good. So H and K are always significant. They're always shifting us left and right, even if they're not technically a vertex, right? They are adjusting our starting point in some way. So I'm going to start at 4, 2. I can actually put a point on the graph now. 1, 2, 3, 4, 2. That's going to be my starting point. Okay. Now I'm ready to draw because I have my little idea in my head right here. You guys don't have to do this every time. It just really helps me every time there's a reflection to draw like my starting expectation. And if it flips over, I know where to draw it. So I know that I'm going to start at that starting point, go to the left, end it, go up to the next one, to the left, end it, kind of in that direction. But I need to know how long to make the steps and how far apart to make them. So to draw my first step, the first thing I need to understand is the horizontal length of the step. So I need to know how long to draw it. Somebody tell me which value I'm going to focus on to know how long to draw my step. Mary? Good. The B value. So the B value was half, meaning X is kind of going half the speed it normally goes to get to its Y value. So how long is it going to take us on our graph to make that next move? 2 units. So I'm going to start at my starting point, but go to the left because I drew that little image up there that the reflection affects the graph. I'm going to draw a step that is 2 units long horizontally. Okay? Now I know I'm ready to go to my next step. I know that I'm going to go up from that point because, again, I'm just referring back to the little sketch I have about like the order of the steps should go based on the reflection. And so the thing I need to know is how far apart is it from this step to the next step that I want to start. So somebody tell me where I'm going to look to determine that information. Sammy? Good. Okay. So I'm looking at the A value, it's 3, and luckily the A values are a little simpler, right? If the A value is 3, the steps are 3 units apart, okay? It's a lot more straightforward. So where this step ended, 3 units above it is going to be my starting point for my next step, which again is going to be 2 units long horizontally, and I can just keep continuing that pattern. So I get a graph like this. Now, I'm not saying it was easy to graph that. We had to have a lot of knowledge in our head, right? But when you looked at this equation, is what we just did, in my opinion, like 15 times better than trying to plug points into this and figure out where the next endpoint is and stuff like that. Okay, because you don't know when that next integer is going to pop up. So I'm not saying plugging in points is bad. I'm just saying it's not the most useful technique. So we're trying to learn these transformations and what the basic graph looks like, because if we have that knowledge, we can graph it really fast. And if you were ever having doubts, you could always go plug in a point and kind of check that you're landing in the right place or something like that. But we can't rely solely on that for all these different random shapes, or else we'll miss parts of them and stuff like that. Okay? So go ahead. Yeah. So the B value was 1/2, which meant our steps were 2 units long horizontally. Is that okay? Okay. So again, this is the one place you can't think about it like slope. You really have to separate the transformations. B is strictly controlling horizontal length of the step, and A is strictly controlling vertical. You're used to looking at A and B together like an absolute value, like how you can factor it out. And so you can do like rise and run. But here, our rise and run, we can't factor it out and put them together. They remain separate. And so that's why one is controlling the rising and one is controlling the running, or one's controlling the vertical and one's controlling the horizontal. Okay, go ahead and take a few minutes and see if you guys can fill in the characteristics below. So your H and K, your X and Y intercepts, domain and range, stuff like that. Okay, so what did you guys get for your H and K values? 4, 2. And X intercepts? None. Y intercept? So 8 right up here, okay. It's the only place that we hit the y-axis, so 0, 8. If it was not on your graph, your y-intercept, how could you find it? Plug in values. What value specifically? 0 for x to see what y equals. It's harder to solve it the other way, right? Like plugging in 0 for y here would be a little bit crazy. Okay. What about our domain? All real numbers. Okay. The domain for these is always all real numbers. There's no limit on what we can plug in. We can plug in anything. Okay, it just rounds. And that's how you'll know if you graphed wrong. If your steps are separated and you can find an x and you don't have a piece of the graph that it corresponds to, then you probably didn't graph it correctly, because every x should have a y value that it produces. All right, our range. So a lot of you guys have a question on range. So could you say all integers this time? No, it's not every integer. It's like every third integer, but not really. You have to start at a certain point and all this kind of stuff. So we are going to actually write it when they end up like this and we can't describe them. And it's like sometimes you'll be able to say odd integers, even integers, right? Multiples of 3, things like that. But when there's not a way to describe them in that fashion, we need to write a little equation that describes them, because the problem is it's a thing that's infinitely long. So we don't really have another way to explain it except for like, hey, this equation, and you can plug in all this stuff to it. So we're going to take a pattern of numbers and write an equation from it. So the numbers that we do see on here, we hit -1, and then we hit 2, and then 5, and then 8. Is everybody seeing where I'm getting that from? Like these are the y values of the branches that we plotted. And then there's infinitely in both directions. Okay, so my first question is, how much are these numbers changing by? 3. There is a consistent change of 3. So if you go every 3, okay, you will reach these numbers, but only if you start at one of these to begin with. Does that make sense to everybody? It's like having stones laid out across the river or something, and I want you to hit certain ones, and I tell you it's every 3, but you don't know if I started on the first one or the third one or the second one or something like that. So I need to give you a starting point, and then I need you to allow you to go every 3. Does that idea make sense to people? Okay, so a starting point for us would be any of these numbers. Somebody pick one. 2. Okay, I heard 2 first, so I heard a lot of negative ones. All right, so if we start at 2, and then you're telling someone, go 3 from 2. So basically to 2, you want to be able to add or subtract 3, but could you also add 6 or subtract 6, and would you still stand on a number? Yes, so it's 3 times anything. Okay, so I just pulled that k out of nowhere, right? Just to put something in there that doesn't, an x or a y, something different that doesn't correspond with any of that. But then I have to tell people what they're allowed to plug in for k. Can they plug in like 0.1 for k? No. When we said go 3 as many times as you want, it had to be like whole amounts of 3, right? Like go 3 1 time, or go 3 2 times, or go 3 3 times. What kind of numbers are those that I'm saying? Integers, because we want them to be able to go forward 3 or go backward 3. So we have to make a little statement after this and say where k is an integer. And you either say that like this, k is an integer, like literally the words I just said, or you say k and you do this little symbol with the integer set. That means k is an element of the integers. Okay, either way, it's like a e kind of. Yeah, I mean, I'll give it to you, but that's probably not correct. K equals. Mathematicians are picky. So is this okay with everybody that if your pattern is something you can't describe with a set of numbers that's already defined mathematically, you're going to define it with a little mini equation. And all you need for your mini equation is the starting point and the separation between them. But people need to be able to go that separation as many times as they want. Okay? All right. Where were we at? So that's our range. So y equals, and you can say it either way, 2 plus 3k or 3k plus 2, where k is an integer. Okay. All right, increasing interval and decreasing interval, none, okay? Our steps are constants. Is it 1-to-1? No, these will never be, right? Those horizontal steps are violating all of those rules that we set up for that. Our rate of change and axis of symmetry are something we don't study for this function. And just a heads up for testing, I told you guys there would be charts, like when you graph things, we'll ask you the same things on this chart. If it has an NA, like it's totally not something anyone's even discussing about this, we will not include those in the chart, okay? Compared to where it says none, that is something that someone might ask you about this function and you should just be able to identify it doesn't have one versus like that's not even something that would be discussed with this function, okay? So minimum and maximum, because they're infinite, none. And then the asymptotes are not something that is studied with this type of function, okay? Do we feel a little bit better about greatest integer function? Okay, so you're just going to take apart the equation.